Hey everyone, in this video we're going to look at now solving trig functions algebraically. So in the last learning intention we looked at how we can use our calculator to do it, but we also do need to know how to do it algebraically. So when we use calculators we get approximate decimal or numerical solutions to trig equations. So when we were doing it on a calculator before, remember all our answers were decimals, so 0.45 for example. But sometimes exact solutions are needed in terms of pi, and these arise when solutions are multiples of pi on 6 on pi on 4, and exact solutions obtained using algebra are called analytical solutions. So we use the periodicity of trig functions to give us all the solutions in the required domain, and remember that sin x and cos x both have a period of 2 pi, and tan x has a period of pi, which we have explored recently. So for example, consider sin x is equal to 1. We know from the unit circle that a solution is x is equal to pi on 2, because we know this point here is 0, 1, right? And sine is always our y coordinate. However, since the period of sine x is 2 pi, there are infinitely many solutions spaced 2 pi apart. So the solutions to sine x equals 1 are actually x is equal to pi on 2 plus k 2 pi. And that's because we can go round once, like this pi on 2, or if I just go make this a little bit smaller, we can also go round and back, okay? And so if we made k1, that would be pi on 2 plus 2 pi. And then we could go around again, plus around again, and we could go on and on and on forever and get infinitely many solutions. So in this course, we'll be solving equations on a fixed domain. So what that means is people will give you a domain, so it might be between 0 and 2 pi, 0 and 3 pi, or something totally different. And that means there'll be a finite number of solutions. So what I'd suggest writing down from this is probably just this bit here and just the diagram, okay? So this is what our unit circle, which we all got, it's all laminated for you, bright orange, is going to be very, very, very handy. And just remember one thing that I just want to point out is that, so here's kind of got two unit circles. This is your pi on 3 and pi on 6. This is your pi on 4. Okay, on ours we've got it all combined. Just remember here that they've got 1 on root 2, where we know that as root 2 on 2. So just remember that it could be either one of these. So when you're looking at the solutions, if you're getting this, that's also equivalent to that. And so that'll be the same answer. Okay, so let's have a look at some examples here. So in this first question, you've got solve for x on the domain 0 to 2 pi of cos x is equal to negative root 3 on 2. Okay, so there's a bit going on there. Now, what we need to look for is where is cos x equal to negative root 3 on 2. So if we have a look, remembering cos x is our x coordinate. So if we have a look at our unit circle, which we should all have in front of us, we should see that cosine of that is going to be 5 pi on 6 and also 7 pi on 6, right? So what we should do when we're solving these questions is we should always sort of draw out, just it needs to be sketched, it's nothing fancy. So a circle, so we've got this, okay? We now can see using our unit circle that we've got 5 pi on 6, okay? And then we've also got 7 pi on 6. All right, so we can go around here, so we've got 5 pi on 6, and I'm sure you'll have more room when you do it, but we'll say that's 7 pi on 6, okay? And this works nicely because we've got a domain of 0 to 2 pi, so it's easier to see. As things get a little bit trickier, it can be a bit harder. And so therefore we can say, well, x is therefore equal to 5 pi on 6 and 7 pi on 6, okay? We look at b, it's a little bit different here, so we have to kind of work this a little bit more. So let's use some algebra to get sine x by itself. So if we do that, we've got 2 sine x is equal to 1. So what I've done is move that 1 to this side, and therefore we've got sine x is equal to a half. So again, we go and have a look on our sine diagram, not our sine diagram, sorry, our unit circle. And so remember that, I'll just write it here, so cos x, let's not do cos x, let's just go cos and sine. So remember you've got x and y. So we're looking for a y coordinate that's equal to a half. So if we have a look on there, hopefully you can see that we've got, so again, just kind of draw it out. You can see here we've got pi on 6. And then if we come across, you also see that we've got 5 pi on 6. Right, so therefore we can say that we've got x is equal to pi on 6 and 5 pi on 6. Okay. Now when we look at tan, it's a little bit trickier, right? So if we have a look at tan here, so we've got tan x, you can see is going to be root 3. Make that negative root 3. Okay, so tan is quite a bit trickier, and what I'd suggest when doing this is you can use your calculator, and what you could also do is go back through your book, because we would have created tables of what sine, cos, and tan were equal to at all the different values on the unit circle, and see if you can go find that. And what I might do is I might also find that and I'll pop that on OneNote as well. But let's imagine here that we're going to say, well, we've got x is equal to tan to the negative 1 of negative root 3. Okay, you will need to make sure your calculator is in radians for this to work, but what it's going to spit out when you do that is you're going to get negative 1 on 3 pi, which can also be written as negative pi on 3. Now, if we think back to everything we've talked about with the unit circle, right? So we've got the unit circle here. Remember, all the positive angles go this way, all the negative angles go this way. So what this negative pi on 3 means is if we have a look at this here, this is going to go basically negative, well, it's going to go pi on 3 downwards, right? So if we think about where is that on our unit circle, if we're having a look, if we're at 2 pi, we're coming down, or at 0, we're coming down pi on 3, that's actually going to be equivalent to 5 pi on 3. Okay, so going down by pi on 3 on the unit circle is actually equal to 5 pi on 3 on your unit circle. Now with tan, and I should have probably spoken about this earlier, remember that our all silly turtles crawl. So what that means is tan is positive here and here, but it's actually, we want tan when it's negative, right? So tan is negative here, which makes sense, and also here. And if we remember with tan from what we've done before, the second angle is always directly across, okay? So directly across in terms of these pi on 3s, and you'll see there that if we have a look at our unit circle where the equivalent one is, come around here, that's going to be equal to 2 pi on 3. So therefore we can say that x is going to be equal to 2 pi on 3 and 5 pi on 3. Okay, so again, tan's a little bit harder. You can definitely use your calculator to help, or go back through your book and find that table of what all your tan values are at the corresponding, values of pi on 3, pi on 4, pi on 6, and that kind of thing. Okay, let's have a look at this example. Something a little bit different because we've got this cos squared term. So in this case, we've got cos squared x is equal to a half on the same domain. So 0 to 2 pi, so just that full rotation, that first time around. So let's simplify this a little bit. So we've got cos x instead of squared is going to be equal to the plus or minus of square root a half. Now if we simplify that further, we know we can say that we've got this. Now the square root of 1 is just 1, right? So that's equal to plus or minus 1 on square root 2. Now I just want to touch base on this plus or minus. So obviously if you've got positive 1 on root 2 squared, that's going to be equal to 1 on 2. If you've got negative 1 on root 2 squared, remember that's equal to negative 1 over root 2 times negative 1 over root 2. So that's going to give us negative 1 times negative 1, which is going to make it positive, and root 2 times root 2 is 2. So that's why you need to have that plus or minus there. So in this case, we need to find where we've got 1 over square root 2. Now remember on our unit circle here, we've got this whole idea of 1 over root 2 is equal to root 2 on 2. So we need to go and find all the scenarios where we've got this. Okay, so again, draw out your unit circle, and if you think about it here, we've got a positive and a minus version of cos, and we know from ASTC that cos can either be positive or negative, and you actually have a look, if you're looking for all the positive and negative ones, you're going to find that they're in every quadrant, and it's pi on 4, okay, then we've got 3 pi on 4, come around again, we've got 5 pi on 4. And if we come around one more time, whoop, we have 7 pi on 4. Okay, so we can therefore say that x is equal to pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. Okay, so let's have a look at this example. Sorry, there's this little self-tutor thing there. Ignore that. So here we've got solve for x between 0 and 2 pi of cos 2x is equal to 1 over root 2. Now this 2x causes us a little bit of drama, nothing crazy that we just have to deal with first. So if we think about an original domain of 0x 2 pi, now it doesn't quite work because we've got 2x. Okay, so what we then need to do is times everything by 2 because we need to make this match this. So times 2, and times 2. So what we're left with is 0, 2x, 4 pi. Okay, and so what that means is we actually need to go around twice. We need to go between 0 and 4 pi. All right, so forget about the 2x for a second. And now we're just going to look at where is cos 1 over root 2. And we know that that is also 2 root 2 on 2. So again, if we kind of have a look at our unit circle, where is that? We know that's going to be here at pi on 4. And also if we come round, we know it's also going to be here at 7 pi on 4. Okay, now that's only going around once. So that's going from 0 to 2 pi. And so that means we have to go again. And if we go around again, so remember, imagine we're now at, so we've gone around once and we're back at 2 pi. We're going to add another pi on 4 there. So if you think about, well, 2 pi is also equal to 8 pi on 4, right? But now we're going to add another pi on 4. So let's just start writing down our answers here. So our answers so far, we've got pi on 4, 7 pi on 4. And then if we go round to 2 pi, but then add the extra pi on 4, right, we're going to end up with 9 pi on 4. And if we're at 8 pi, we're going to add 7 pi on 4 again, because we're going to go around and add that one again. We get 15 pi on 4. Okay, so I hope that makes sense there. However, this is actually, instead of it being x, remember we've got 2x, so this is actually 2x is equal to this. Okay, and so then to get x, we need to divide everything by 2. So what that means is we're going to get pi on 8, because pi on 4 divided by 2 is going to give you pi on 8, because it's 4 times 2. We're going to get 7 pi on 8, 9 pi on 8, and 15 pi on 8. Okay, so there's that little bit of an extra step there in this case where we have to change the domain to match the 2x. Then we get our solutions in terms of 2x, and then to get our actual solutions for x, we divide everything by 2 in this scenario. Okay, now let's use that same logic here to have a go at question B. So B, we've got sine x on 2. Now another way that could be written is sine a half x. So in this case, when we're looking at 0, x, 2 pi, we're actually going to times by a half. So what that means is we're going to have 0, half x, and pi. So in this case, we're only going between 0 and pi. And we're looking at when sine is equal to root 3 on 2. So if we have a look at that, hopefully you can see here. So if we draw this, we're going to have a look. So sine, we know, is our y coordinate. So it's going to come up to here, and we're going to have pi on 3. And if we have a look, you'll also see that root 3 on 2 is also here at, 2 pi on 3. Okay, and because we're just going 0 to pi, this is where pi is, so they're the only two we need. So therefore we can say we've got a half x is equal to pi on 3 and 2 pi on 3. But we haven't quite finished yet because we need to get rid of this 2, right? And so to do that, we need to times everything by 2. So what we're left with is x is equal to 2 pi on 3 and 4 pi on 3. Okay, so a little bit trickier there, but I hope that makes sense. Okay, final example, I promise. So in this one it says find the exact solution of square root of sine x is equal to cos x. Okay, so a little bit different here, but hopefully you can see you've got a sine and a cos. And if we can kind of put them together, right, remember that we then can make tan. So if we have a look at this, imagine we've got, let's make it so we've got sine x is equal to cos x over root 3. So I've just divided both sides by root 3. And then I want to get sine cos x over to this side. So imagine I'm dividing both sides by cos x. So imagine dividing by cos x and cos x. And if I divide there and divide there, well, they cancel. So therefore I've got sine x on cos x is equal to, now we've got to be careful here, okay? It's going to be equal to, you've still got that root 3 on the bottom, doesn't just become root 3 by itself. Because we've cancelled that cos on the top, it's just left with a 1. So we've got 1 on root 3. Now we can simplify sine x over cos x to be tan x, right? So tan x is equal to 1 over root 3, okay? And again, let's use our calculator. So x is going to be equal to tan to the negative 1 on root 3. If you pop that in your calculator, you should get 1 over 6 pi, which you can also say is pi on 6, okay? So when it says it's pi on 6, let's have a look. So if we have a look on here, pi on 6, we can see that that's there. Now remember with tan, it's directly across. We always go directly across. So the equivalent of the pi on 6, that's kind of terribly drawn. Come around. If we have a look on our unit circle, it's going to be 7 pi on 6. So therefore we can say that we've got x is equal to pi on 6 and 7 pi on 6. But before we are happy with that answer, something we didn't talk about was the domain here. And the domain here is in degrees. So because it's in degrees, let's convert these back to degrees, and luckily our unit circle can do that. And so you'll see you've got 30 degrees and 210 degrees. So just be careful of that. Make sure you're looking at exactly what the question wants in order to answer it correctly. Okay, so I know that that's a little bit more complex than what we've done, obviously solving with a calculator, but I hope that helps, and we'll go through some in class. And if you've got any questions or concerns, let me know.